Okay, so good afternoon, everyone. So this is the lab for week 8 about nonlinear equations. And we will study 3 methods: bisection method, fixed point iteration, and Newton method. Okay, so we do it step by step. So bisection method. So now we are asked to write a function that implement bisection method. So the function will have this form, okay? So take in a function, the left and the right hand side, some tolerance, and give out the solution and the number of iteration, okay? So we do bisection first. So let me share my MATLAB screen. So let me clear everything. Okay, so now we edit a new function called bisection. So bisect.m doesn't exist, so I can write here. So bisection is a function. So return p and return the iteration. So bisection take in a function f, by f string, and a and b are two numbers, left and right ends of the intervals and some tolerance. Okay, so we write some brief description of the function. So solve fx equals 0 by, or maybe using bisection method. Okay, and we return p when fp in absolute value, okay, is less than the tolerance, maybe less than or equal to tolerance. Okay, and after iteration, after that number of iteration, ite number of iterations. Okay, so now first we have to check whether we can use bisection method or not. So remember, if FA and FB are opposite sides, then you can use bisection method, right? Otherwise, you cannot use it. So if FA and FB are opposite sign, okay, then you say that we cannot do it. So maybe you say that, okay, P is not a number. So we check if it's not a number, then it means that you cannot solve it, and number of iteration can be -1. Okay, so we can add into the description that return not a number and ite is -1 when there is no solution. Okay, so now so if the opposite ends, they have the same signs, then FA times FB will be positive, right? And then we don't do anything. So else, okay, so now what is the next thing we have to check? So what is the next thing we should check? So remember, suppose A or B are the solution, then we don't have to do anything as well, right? So suppose A or B maybe A first, yeah. So absolute value of FA less than the tolerance, okay, less than or equal to the tolerance. Then solution is just equal A, right? I mean, it happened that the endpoints could be the solution, so P equal A. And we don't have to do any iteration, so iteration just equal 0, okay? And, I mean, you can check the same whether the other ends is a solution already or not. So if absolute value of FB less than the tolerance, then okay, so we just quit. Okay, we say that the solution is called B. We don't have to do anything. Iteration equals 0. Okay, so now we check on the condition already. Okay, so now it's time to do the bisection method. And if you remember bisection method, first you have to divide the intervals into two subintervals. Yeah. So we do that by compute the midpoint. So the midpoint is just A plus B divided by 2. Yeah. And now how many times we have to do the iteration? So do we know how many times we have to do the iteration? Anyone? So do we know how many times we have to do the iteration? Somebody say something. Tolerance. Well, tolerance is we don't know. See, the answer is we don't know exactly how many times we do the iteration. Yeah, so we keep iterate as long as f of the midpoint is still less than the tolerance. I mean, sorry, still bigger than the tolerance. Yeah. So we don't know. So we just use the while loop, okay, instead of the for loops. Yeah. So while f of the midpoint, and remember, do not forget the absolute value because we need to check the absolute value. It could be negative. We as long as the midpoint, okay, is still bigger than the tolerance, then we keep doing it, right? So we're doing what? So remember what is the, you see, so now you see, so it get a midpoint, yeah? And if this condition doesn't satisfy, then I mean it found a solution already, right? So you can return, P equal midpoint here. And iteration, I mean, well, here we check, we have to set iteration equal 1 because you compute one midpoint already, so one iteration already. But what happens if it doesn't satisfy? Well, what happens if it's not a solution? Well, so remember the algorithm, right? So now you check if the left intervals, yeah? So now check the left intervals, whether the function is of opposite sign. Okay, so if it's opposite sign, yeah, then what do you do? And otherwise you have to check, I mean, the right intervals, the other half. Okay, so you have to check the left and the right subintervals. Yeah. So now remember, if the solution is in the half intervals, what do we do? So what do we do here? So maybe I should say that, okay, now, yes, B có midpoint, yes. So now you just say that, okay, now you update the, the right hand side, right? So B now is a midpoint. And A is still the same, right? Yeah. Otherwise, if, you know, I mean, the midpoint and the right hand side have opposite signs, then now what do we do? Well, we just say that A now is the midpoint, right? Okay. And now, okay, so now you have a new interval. So now you have to update the, midpoint, yeah? So you have to update the midpoint. So midpoint now is A plus B over 2 again. So remember the midpoint. Okay, I have to end the if here, yeah? So we have to check. So check in the left subintervals, yeah? And here we check in the right subintervals, yeah? And then, you know, you compute a new midpoint. So now you update the midpoint, yeah? So update the midpoint. Remember, because we update the intervals already. So we have to update the midpoint. And do not forget to increase the number of iterations, because every time we compute the midpoint, we increase the number of iteration, yeah? So increase the number of iteration, the number of iteration. Okay. So when it get out from this loop, then you see P will be the solution, right? Because it no longer satisfies the condition for the loop, right? So it's mean that absolute value of f of the midpoint has to be less than the tolerance, and that's it. Okay, so see whether it runs or not. Well, we have to check. We have to make a new script, you know, to test the bisection. Yeah. So now I will make a function. So what function you want me to test? What function? So remember, I will call the function like this. Yeah. Bisect f a b tolerance. Okay, but now you have to give me the function. So a equal, b equal, tolerance equal. So say tolerance is 10 to the minus 6, yeah? So what function we should do now? Any suggestion? The tolerance will decide how many iterations, but it depends on the function as well. So we don't know exactly how many iterations it can run. Okay, it just run until the absolute value of f is less than the tolerance. So the number of iteration depends on the tolerance and depends on the function f, and that depends on the intervals you are looking for the solution as well. Okay, so there's many factors here. So what now give me the function? Anyone give me a function that you want to find 0? Okay, good. Exponential x minus 2. So exponential x minus 2. Yeah. So then what is the intervals you want me to look for the solution? Okay, so minus 2 and 2, right? So minus 2 and 2. Okay, so we run it, and suppose we found a solution, we print out the solution here. Solution P equal, say, a floating point after iteration, yeah, and we put in P and iteration. Okay, let's see whether it works or not. Okay, so we have to test it. And now let me run it. So I save it and run it. So I have to save it here. Well, so I need a name. So I just put in test bisect.m. Okay, so I have this one, it tests bisect.m, yeah. No. I don't have to write .m. Okay, so I found a solution. So how do we know this is correct or not? Well, solution of e to the x equal 2 is just logarithm of 2, right? Yeah. So it is close. Yeah. So remember, log here is a natural logs. In MATLAB, if you write log means natural logs. Okay. So logarithm of natural logs of say e to the 1 is just equal 1. Yeah. And if you want logarithm 10, then you have logarithm 10 of, you know, a number like this. Yeah. And I think it has logarithm 2 as well. So logarithm 2, yeah. So logarithm 2 of 1024 to 10. Okay. But you see, so this works, yeah. And it's very fast after 21 iterations. So what are the functions you want me to test? And you see, in this case, what is the difference between our solution and the exact solution? Well, so about 4 times 10 to the minus 7. Okay, so that is within the tolerance. So we want the the function has to be less than 10 to the minus 6. Yeah, so it's like something 10 to the minus 7. Okay, so that is bisection method. Okay, so now we move to fixed point iteration. So any question about this one? So go back to bisection method. Yeah, so this one is the algorithm. Yeah. So no question about this. Okay, so we move to fixed point iteration. So now fixed point iteration. So remember here we have to solve gx equal x, and it has the function g, the initial guess, the tolerance, and the number of maximal iteration. Okay, so we can cut and paste the whole thing here. Okay, let me cut and paste the whole thing here and put in a new okay, so a new function. So the function is fixed points. Yeah. So like before, you can do some check, initial check. You know, like suppose, well, we set p equal p0 first. Yeah. Okay, and if p0 is a solution already, then we don't have to do anything. And remember, when it means it's a solution, then we have to check absolute value of g of p minus p. Okay, less than some tolerance. Then, okay, we say that I'm going out. Okay, so I just p equal p, iteration equals 0. Okay. Otherwise, I'm start doing the fixed point iteration. Okay, so now what is the algorithm? So we just do for iteration equal 1 to maximal number of iteration. By the way, you know, those comments, you know, when you type help, then it will display it. So suppose help bisection, you know, bisect, then you see it will show you exactly the comments. Yeah, so it's good that you give some description. So after a year or 10 years, you look at back and you remember what you have done. Okay, so now go back to this. So for iteration equal 1 to n, so in this case, because we are given that the number of maximum iteration is n, so we just use the for loops. Yeah, and then now we implement the fixed point iteration. So p equal g of p, right? G string, because we specify the function like this. So remember, the formula is x n plus 1 equal g of xn. Yeah, so we just implement this formula. And then, okay, we check whether it is a solution. Okay, so now I'm going to check that whether my new p is the correct solution. Okay, so if it is the case, then I just stop, right? I just stop. So I just break. And now p, so p is returned anyway. So we just break from the loops. And now after n iteration, if you cannot find the solution, okay, so now what happened if after n iteration, okay, so suppose after that many, well, maybe we should be generous, less than or equal the tolerance. Yeah, so less than or equal the tolerance. So if it's bigger than the tolerance, when we say that, okay, we cannot find a solution. So, and we say that by setting p equal not a number, okay, and iteration is -1. Okay, so that's it. So now we need to save it and we have to test it. So fixed point, yeah, so fixed point. And now we have to test this. So test. Okay, so now f is, so this one in the question, it is given. So the question say that we should choose. So let me get my question. So the question say that, so this is question number 3. So the question suggests that we should use sine 2x. Okay. And then you should take the intervals. No, we don't have to set up an intervals here, but we need to set up a initial guess. Initial guess is 0.5. Okay. And then we have to set a tolerance. So the tolerance is 1 e minus 8. So 10 to the minus 8. Yeah. And then that's it. So you just run it. So p ite equal, okay, fixed point. Well, maybe this is a function g instead of f. Yeah, we set g. Yeah. So we give G, and then we give, so what is the next argument? So the next argument is B0 tolerance, B0 tolerance, and the maximal iteration, maybe just give 100, okay? Then after that, you print out the solution as before. So F print F. Okay, so you print out iteration, so fixed point iteration method with tolerance something. So tolerance equal something like this, and then an initial guess P0 equal a floating point number, so 1.2, so 1 digits before the dots and 2 digits after the dot, and then you put in tolerance here and P0 here. Okay, and then after that you print out the value of P. So P equal, so you want to print out a floating point number, okay, and you want say 1 digits before the dot and 9 digits after the dots, so or 8 digits after the dots, yeah. Found after that many iteration. Okay, so then you put in P here and number of iteration here. So we got a new line, we got a new line here, a new line here. Okay, so see whether we can run this. So I have to save it first. So test fix. Okay, so for fixed point, yeah. Okay, so first you see that help fixed point. That show me, you know, what are the input, what are the output of the function. Okay, so, and now we run it. So now test fix. See, so we found the solution. So GP, so remember GP has to equal P. So GP, okay, so GP absolute of GP minus P. Okay, so 7 10 to the minus 9, so less than the tolerance. Yeah, so this is how we implement fixed point method. So this is the key formula. Okay, so x n plus 1 equal gxn, but because we reuse the variable, so we just put everything in P. So you apply to P, and then so you get out the new values and you put in P again, and you just check whether less than the tolerance. That's it. So any question about this? So now what happens if we try the function, you know, exponential x minus 2, like the previous question? So now what happened? So suppose now I want to solve fx, sorry, I want to solve fx equal e to the x minus 2, right? Equal 0, right? Yeah. And so as the function, I mean, as so one way to convert it into a fixed point iteration is you can do many things. You know, you can plus x on the left and on the right. Yeah. Okay, so you essentially just the same like this, yeah. And then, so the function g will be exponential of x minus 2 plus x. Okay, and see, we should run it again and see whether we can find a solution like we have before, right? So now test fix. Should it be tolerance break? Sorry, in what form? So in the fixed point, if absolute less than. Well, it depends. You see, like, because here we say that less than or equal the tolerance. So it's up to you. Yeah. So, I mean, you can say that it's less than the tolerance, but you can say less than or equal. Is it your question, or? I mean, if you say that strictly less than the tolerance, then here we just said greater or equal. But I think this is okay to be less or equal, yeah. So, you say that we should move p equal g string p after the condition. Good point. Good point. Yeah, maybe we should do that. Yeah, we should define the. Yeah. Okay. I think it makes sense. Yeah, to do that. But I think the number of iteration will be a bit different. Let's check. Okay. I mean, okay. Let we check. We just move this to after the if. I think it will find the solution, but maybe iteration will increase by 1. Yeah. Okay. So suppose I do like this. Yeah. And I think it's okay. I mean, it's not a big problem. Yeah. So now suppose you want to go back to this. Then we run it again. Yeah, so increase the number of iteration. Yeah, just increase by 1. I think it's okay because it depends on how you define the iteration, right? I mean, as long as when you break, then what number the iteration is, it will give you exactly that value. Okay, but it doesn't change the solution. Yeah, so the solution is still there, but the number of iteration is just increased by 1. Yeah, so it's not very important. I think the solution is more important than the number of iterations. Yeah. Okay, so now we go back to we can leave it like this. Yeah. Okay, so now suppose I want to change the function. Yeah, I want to change g to be this. And then I run it and see whether it works or not. You see, so now it doesn't work because, before you have a function that gives you a solution, but now it just blows up. But it's just like after 100 iteration, it doesn't find a solution. Okay, so now can we try another one? So we see now you have e to the x equal 2, right? So what means that x equal logarithm of 2. Well, but then there is no fixed point, so there is just logarithm of 2. So logarithm of 2 is not a function. So can we define logarithm of 2? Okay, so suppose we put g just equal logarithm of 2, okay? So see whether it works or not. So it's always equal logarithm of 2. So I save here. Oh, so it works. So then you see, so it depends on how you define the function g, right? But in this case, why it doesn't work? Because now remember, if you take the derivative, yeah, then it will be, in this case, the derivative will be exponential of x minus or plus 1, right? And if you put in the solution, so g prime of x star, what is the solution? Yeah, so of p star. Okay, in our case will be g prime at the point logarithm 2. So it will be exponential of logarithm 2 plus 1, which is 3. And remember, for fixed point iteration to work, you want g prime at p star have to be. So what is the condition? Remember, what is the condition? So for fixed point, yes, less than 1. So for fixed point iteration to converge, you want, you know, g prime at p star has to be less than 1 in absolute value. You see, so when you define the function g, you know, it's not always true that you can have a convergence to the solution. Okay, so it's very dependent on the function g, and what you want is g prime at p star has to be less than 1. So you see, if it's a constant, then you take the derivative, it's equal 0, definitely less than 1. And in the first case, you know, if you have the first case here, yeah, so if we go back to this one, so if you run it, right, so you get a convergent convergent. And why is that? Well, because what is g prime in this case? So g prime is 2 cosine of 2x, yeah. And what is g prime of p star? Well, we don't know exactly p star, but we know p star is very close to this value, right? So you put in this value, and you put in cosine 2 times this value and multiply by 2. Okay, then you see that this quantity is less than 1 in absolute value. Okay, so in absolute value, this one is less than 1. So that's why you have a convergence after, you know, a finite number of iteration. Okay, so 0.638, whatever, yeah. Okay, so we stop here and we move to Newton method. Okay, so the next one will be Newton method. So Newton, so again, so let me cut and paste the description of the function. So Newton method is given in this description. Okay, so the function name is Newton, and the input is f and derivative of f, initial guess, tolerance, and n. Okay, so we do exactly like before. We say that, okay, so P equal P0. So if F of P, sorry for the new P, should be in front of the if statement. Well, before you want after the if statement, but now you want in front of the if statement. I think it will change the number of iteration, you know, just by one, yeah. But you still get the solution, yeah. Okay. It depends how you count the number of iteration. Yeah, yeah. Okay. So well, I mean, if we move before the if, yeah. So it means that you make one iteration already, okay. And when it break, then it count that iteration, yeah. So that's why I say that it just depends on how you count the number of iteration, right? So because when it break, then you know whatever the number of iteration, it will keep that values, yeah. Okay, so now we go back to Newton, yeah. So Newton then, so if f string of p is less than absolute value f string of p less than the tolerance, okay, then we don't do anything. We say that, okay, iteration equals 0 and I return p. So p is there already, yeah. Otherwise, okay, exactly like before. So now you do n iterations. So iter equal 1 to capital N because we want the maximum number of iteration, yeah. And here, remember the formula for the Newton method. So P equal P minus F of P divided by F prime of P, okay. So remember this, the formula. So the formula is Pn plus 1 equal Pn minus F of Pn over F prime of Pn, yeah. So I just use this formula, but I just override to the variable P again and again, okay. And now I check, okay, so if I do exactly the same here. So if the value of P satisfy the condition that absolute value at that point less than the tolerance, then I break, yeah. So I have the solution already. I don't do anything. And whatever the number of iteration, it just return, yeah. Otherwise, you see, after we carry out an iteration, right? If this condition is still not correct, yeah. So if the value of the function f of p in absolute value is still bigger than the tolerance, then I say that, okay, I cannot find a solution. I say that p is not a number. And then, you know, I quit. So this is identical to the fixed point iteration, except this line, okay? Before you saw that in a fixed point iteration, p just equal g of p. But here we just have p equal p minus f of p over f prime of p. Okay, so that is exactly the same, right? Okay, so now we have to test this. So now we have to save this first. So save at Newton. And now the next question is, we will check Newton method. So now you see that we are given the function. Well, so first the question say that plot the function first. You plot y equal sine 2x minus x plus 0.5. Okay, so you define f to be sine 2x minus x plus 0.5. Yeah. And now I want to plot it. I want to plot it first. Yeah. So I want to plot it. So x plot we equal in space plot from 0 to 3 and maybe say 1,000 points. Yeah. Then I plot it. So I plot x plot f of x plot it on. Okay, so if I plot it, what do I see now? So if I plot it, run, I have to give a name, so test Newton. So you can see that. Okay, so let me show you the plot. So the plot look like this, yeah. So you can see that the function is going down and going to cut OX at about 1.18, and then it go down again. So we know that there exists a zero, right? In that interval from 0 to 3, yeah. But now we want to use Newton method to find out what the solution is. So now I want to find the zero using Newton method. So this is question 1. This is question 2 here. So now the tolerance is 1e minus 8. So as before, so 10 to the minus 8. And then the initial guess is 1.5. Okay, and now we call Newton method. So remember, how do we call Newton method? So help Newton. So you will see that so we have to give a f. So output is p number of iteration and Newton f. Okay, so it asking for df as well. So we haven't computed df. So df is the derivative, yeah. So p0 tolerance and maybe 100 for the maximum number of iteration. So now we need to compute the derivative. So derivative, you know, I mean, you can use symbolic package, but I think for a simple function like this, just use it. Just use, you know, pencil and papers, because symbolic package will be very slow. So the derivative of this one is just 2 times cosine of 2x minus 1, yeah. So then you put function f, the derivative, initial guess, tolerance, and maximum number of iteration. And then you print out the message. So f print f, Newton method with tolerance, tolerance and initial guess. Okay, so you put in tolerance here and initial guess here, P0 here, yeah. And then you print out the solution. So P equal 1.8f, it's a floating number, after that many number of iteration. So you put in P, you put in number of iteration. Okay, and see whether we can run this. So we run this. So suppose I save it and I run it. So test Newton. You see, so it found a solution after 4 iterations. So 1.1900 something. And you can check it is a solution, right? Because if I put in F of P, then it close the machine errors. So 1 times 10 to the minus 15, yeah? And after only 4 iterations, very fast, okay? And now the next question is the same thing, except that now I need to change the initial guess. So I will do exactly the same, but now, so we'll cut and paste here. Yeah, but the initial guess is now we have 0.5. Okay, and see what happened. So now I save it. So see, the only difference is before you have initial guess is 1.5, and now you move the initial guess away, you know, to 0.5, and see what is the effect. So you run it again. So you see, the first initial guess give you the solution 1.19, but the second one, after 100 iteration, it doesn't give the solution. So why is that? So it's very sensitive to the initial guess, you see. So why is that? Well, I mean, we have to look at the plot of the function again, yeah. So now if you look at the plot of the function, so now let me make the plot a bit bigger, yeah. So you see that if we start at 0. So here, so this one is the 0. 0 is right here, yeah. It's about 1.1, yeah. So if we start at 0.5, okay. Then remember Newton method, you draw a tangent line, yeah. You draw a tangent line. Then you got the next iteration is here. Then you draw another tangent line. Then it gets closer and closer to the solution. But if you start at 0.5, okay, so now it's become a problem, because now you see when it draws a tangent line, it doesn't cut on the correct place that close to the solution. It will cut somewhere on the left, and then it just going further and further away. So you see that Newton method is very sensitive to the initial guess. I mean, it has a quadratic conversion, yeah, but it is very sensitive to the initial guess. Okay, so we have to be very careful when we use Newton method. So usually they have a, you know, like in F0, they have a combination of inverse interpolation, bisection method, and Newton method. So you use low method to find the correct intervals, and then you put the initial guess in the small intervals, then you use Newton method to get into the solution. Okay. So let me stop the recording. You can ask any question.